All right, good morning. Not worried. I walked in, it was like 8:45, so I was a little bit early, and there were like two of y'all here. And I was very concerned about what was happening here. Mostly I was like, what am I missing out on? Where is everybody? Is everybody else getting to sleep on a Friday? So hilariously, our daughter wants to sleep in on school days. And then I promise you tomorrow morning, she'll be up at 5:45, ready to like rock and roll and ride her hoverboard around the house and do things. Whereas this morning, it's like 7 and we're like, you have to get up. You have to get up. And she's like, no, I want to sleep in. I want to sleep in. She told us yesterday, after having been sick, and then her birthday was last week, she's like, I need a day off. Right? He's just like, it's been my birthday, I've been doing a lot of things, I need a day off. I need a day off. So I asked her what she wanted to do on her day off, and she's like, I just want to relax on the couch. The girl has never relaxed on the couch in her entire existence unless she is sick, right? It blows my parents away, and apparently I was a very sort of subdued and would like play by myself and like quiet kind of child. And Ellis is just all over the place all the time. And we're loud and we're dancing and we're singing and we're yelling at Alexa. Woo. She learned she can ask Alexa to play whatever songs that she wants all the time. It's not great. It's not great. So anyway, that's how my Friday morning was going. Okay, so do a couple of announcements before we actually start today. We are officially moving the test, okay, to a week from Monday. All right, so 2 Mondays from now, I changed it in Canvas, so the date in Canvas has been changed, okay? So that's when our test will be. My hope is that we will finish this stuff today. On Monday, we'll do sensory motor integration, okay? On Wednesday, we'll start some new material, and then on Friday of next week, we'll review for the test. Okay? We're just gonna shift everything, back a day, which is not a huge deal. The new stuff that we cover on Wednesday will not be on the test, right? So that's what we're going with that. If you're Ty and I are doing our best to try, as some of you guys have had excused absences and things, and have had some issues getting like names and stuff on in-class assignments, please keep checking your grades and make sure that stuff looks the way that it's supposed to. If you have some sort of an excused absence, will you let us know? In the future, we're gonna try to copy Ty on all of those. I'm doing my best to get them sent on to him. Just keep an eye on that. Make sure that it looks the way that you're expecting it to. Okay, so that's kind of where we are with those things. I will mention, right, and I'm pretty sure that they're up. There are the lecture outlines that you guys can follow along and try to fill out beforehand or as we are going through things. I was asked about a study guide the other day, and then there should be a list of potential short answer questions. That is on Canvas for the first exam, okay? I will pick 3 or 4 or 5 things from that list, and those will be the questions that you get, all right? Things that are covered in the other questions will also be on the test, they'll just be in multiple choice or something else, okay? So now would be the time to start working your way through some of those, mocking out what you think your answers would be, sharing them with friends in class, seeing kind of how that's going to go. Okay? So those things are there for your benefit. I don't really understand because I'm old how Quizlets and those kinds of things, what they are and how they work exactly. But I have been told that there may be some like publicly available Quizlets from students that have had me last year and in the fall that might be out there that you guys could look for. That would be helpful. Okay. As I also put up the other day, we have a student who was in class last semester that did really, really well. Her name is Maria Newton, who, has expressed an interest in tutoring. If you guys want a tutor or need a tutor or something, I think she'd be able to do a really good job. I put her contact info and her little flyer thing up. I don't know that the tutoring center always has somebody that does our class, but that's also out there. And then I'm always available if you have questions, you need help. Okay? Just want us to be prepared as we near our test. Any questions about that? You feeling all right? You guys gonna crush the first test? Okay, last semester, everybody crushed the first test. It's not a normal thing. And then it went and got worse over time, which was very odd for me. Usually, the first test we don't do so great, and then we kind of steadily get better as you guys get used to how I ask questions and how to study and all of that. So, so we'll see how we do. All right. Any quick bro science? Anybody got a bro science thing? Forgot to ask Ty to text me one. He has a big list of all the things that you guys have. Anybody? Anybody see something? Something on TikTok, something anywhere? You guys are like, ooh, I need to ask about this. Kevin.
Oh, what are your thoughts on taurine?
On what?
Taurine, L-taurine.
Taurine. It's fine. I don't know a whole lot about it. And what are the touted benefits of taurine?
This is supposed to help with brain sensitivity to your strong.
Okay. So maybe it does this. It's an interesting question. What has taurine in it? Emily, is there taurine in your Celsius? Anybody else?
Yes.
With an energy drink, is there taurine in there? Okay. How many of you take pre-workout or have taken pre-workout? Okay. What do you imagine I'm going to say about your pre-workout? Very good, Cody. Did I come to your intro to HES class and say that by chance?
I don't remember that.
Okay. Pre-workouts work. The only thing in your pre-workout that does anything, for the most part, is caffeine. Okay? That's what's in your pre-workout. That's what's in your energy drink, is caffeine. Coffee would work as a pre-workout. Okay? I'm not gonna ask you guys to know how much you pay for your pre-workout. You know how much your energy drink costs. Okay? You can go to Walmart as long as you're 18, and you can buy 100 200 milligram caffeine pills for $4. Okay? Look at your energy drink and tell me and look at how much caffeine is in there. Look at your pre-workout and figure out how much caffeine is in there. And it's probably around 200 milligrams. Okay? So have your pre-workout, the caffeine works. And surprisingly, the caffeine works by improving exactly what we're talking about today. It works in the neuromuscular system, it works in helping you maintain or improve motor unit recruitment. Okay? Of all of the things that we know, creatine works, caffeine works. Everything else, pretty iffy in the midst of these kinds of things. Okay? Pretty iffy. So I don't know, Kevin, I'll have to look into the taurine. Most things that have caffeine also have taurine in them, so it's difficult to. Can you buy just taurine by itself? I'm sure you can, right? Okay. I'll have to see if anybody's done a study on it. All right. So do with that what you will. I'm a caffeine, I'm an addict, I need it, I have to have it, I hate coffee, coffee's terrible, it drives my father crazy, he's a coffee snob. I've tried everything you can possibly put in it, and it is still terrible. So, all right. We left off the other day. Okay, we left off talking about the things that control force production. Why are you as strong as you are? Okay. Why are you maybe stronger or not as strong as your neighbor? And remember, the first thing is, how big are you? How much muscle do you have? Okay, that's one. The second thing we were talking about was, of that muscle that you have, how much of it can you use at any one given time? How much of it can you recruit through your motor units to engage the cross bridges and generate force? Okay? So we'll get into a little bit about what the recruitment order gets us in a second, but I failed to mention this the other day. There is research that tells us, okay, that in a relatively untrained person, your quads, the average untrained person uses somewhere between, they're able to turn on between 75 and 85% of their quads. Okay? So that means that when you do training or something, you've got some room to be able to improve your recruitment in there. Okay? Weirdly though, when you look at, say, biceps or soleus or your plantar flexors, an untrained person is more like 90%. They're able to activate about 90%. Very well trained people are going to be on all muscles that they've trained, probably somewhere north of 95%. Okay? Big muscles that are strong, if you're not trained, tend to have more room for improvement. Okay? Because you just don't need to do a maximal contraction at all. Right? You carry your body weight around, you go up and down stairs, right? You don't have to max out your quads quite as much as you would, say, your biceps if you're carrying groceries or doing something else, right? Because they're small, their ability to generate force is less, and so what we do in our everyday lives tends to be a larger percentage of max. Okay? So does that part make sense? I wanted to kind of throw those numbers out to you guys. So when we start talking about what's the response with training and stuff, that's what we'll get into next week on Wednesday with the new stuff that we can have a kind of a start. Okay. So the last thing we covered on Wednesday was recruitment order. When you go to pick something up, right? I'm curling up my bag. I start off with the smallest motor units that have the fewest muscle fibers. Those fibers are slow twitch. So the smallest ones, and I go 1, 2, and I keep adding until I get enough force to overcome gravity. Okay. As the weight that I have to move gets heavier and heavier, I have to turn on and recruit more and more motor units. They're going to go from type 1 or slow twitch to 2As, and then if I need to get closer to maximal force, that's what I'm going to call in the 2X fibers. Okay. So there is an adaptive advantage to all of this. Recruiting slow ones first is good because they're resistant to fatigue. Okay. Your slowest motor units in any muscle are always going to get turned on basically anytime you do a contraction. Every time I walk, I turn on the slowest, smallest motor units in my quads, right, in my calves, in my TAs when I go to pull my toes back and those kinds of things. All right. And I walk around a bunch. Most of us do this all the time. Okay. And so it is adaptively beneficial that those muscles don't fatigue. Those slow units don't fatigue because we do lots and lots and lots of low force contractions. So that's a positive. Okay. The other thing that it does is it gives us an ability to do small gradations in force, which we're going to talk a whole lot more about in the coming couple of slides. Okay. By doing small first, you're getting these baby increments in force. And it lets us, during low force contractions, have very, very fine control. Okay. Which lets us do things like write and talk, okay, and play musical instruments and sew and things of that nature. Okay. It matters much less when you're doing close to maximal contractions, because think about it adaptively. When might we've ever had to do a maximal contraction 100,000 years ago, right? I'm running, right? I'm running away from some sort of animal that's chasing me. I'm running, I'm sprinting, I'm jumping, trying to chase something else, to hunt it for food or something in that particular way. And so if you can only do that for a couple of contractions, that's a less terrible thing. Right, and so that's the advantage that we get doing this. Okay. I'm gonna add a caveat to all of this, okay, caveat to all of this. This slow to fast, small to large recruitment, we know that it occurs during concentric contractions and isometric contractions. There's some limited evidence that during eccentric contractions, that's not what happens. Okay. And that's all I'm gonna say is that maybe during an eccentric contraction, it's different. It's not necessarily fully reversed, fast to slow, but there's some evidence in cats that it is. When they do really fast eccentric contractions, that they can go fast to slow. We don't have a lot in humans that confirms any of that, but there's something about eccentric contractions that may be a little bit different. Okay. So that's all I'm gonna say. We'll come back and talk a lot more about eccentric contractions with resistance training and their importance with resistance training and how eccentric contractions are the things that make you get sore. Okay, that make you get sore. That's what causes muscle damage. Okay, so that's recruitment order. So to understand the next part of things, okay, the way the nervous system controls and modulates force production, it's not only going to happen by turning on a motor unit or on and off of a motor unit. There's a separate thing that it can do once a motor unit is turned on. Okay. But to understand that, we need to go back and revisit part of excitation and contraction coupling. Okay. And again, this is going to tie what's happening at the signaling level in cognition to contraction back to actual force output and production. Okay, so what I'm showing you guys here is an amount of time or a phenomenon that we call the active state. Okay, the active state denotes the period of time, okay, after an action potential has gone down the T tubule and signaled at the DHP receptor to open the ranitidine receptor. The active state is calcium goes out of the sarcoplasmic reticulum and it floats around inside the muscle fiber for a little bit, and then it gets pulled back in. Okay, so that amount of time from when it's first released to when all of it gets pulled back in is called the active state. Okay. We are only going to be able to initiate cross bridge formation during the active state. We have to have calcium that is released. Okay, we have to have calcium released in order for that to happen. All right. So, in order to understand sort of how and why this works, I want you to look at this graph on the right-hand side. Okay, there are 3 lines on there, and they are time-locked. The top line shows the membrane potential. This is the membrane potential at the sarcolemma, so at the surface of the muscle fiber. Okay, the second one down shows calcium, and then the third one down shows tension or force production. So this is grouping and showing you the timing of, we get an action potential on the surface of the muscle fiber down into the T tubule. We see when then there's a little bit of lag once that happens, and we get calcium to be released. And then once calcium is released, there's a little bit of lag, and we get cross bridge formation, right? And then you will note then as the membrane potential shuts off and goes back to normal, calcium spikes and then it comes back down. And then as it begins to come back down, there's a little lag and then tension begins to fall again. Okay. So think of this as one action potential causes a certain amount of calcium to be released over a very short window of time, and then it gets pulled back into the cell, pulled back into the SR. The thing that pulls it back in, I will remind you guys from the other day, is an enzyme called the calcium ATPase or CIRCA. Okay, CIRCA. Think of CIRCA as a vacuum cleaner. It's a vacuum cleaner, all right? Calcium gets released out into the from the sarcoplasmic reticulum. CIRCA turns on and it just vacuums up all that calcium back in. Okay, CIRCA uses energy and it runs at a particular speed. Okay, type 1 muscle fibers have a slower or a less powerful vacuum cleaner than type 2 muscle fibers. So you can pull the calcium back into the SR faster in a fast twitch fiber or in fast twitch motor units than you can in slow twitch. Okay. And this is going to become important for how we modulate force production as I show you guys the next slide. Okay, y'all with me so far? Kind of, sort of, maybe. All right. So I want to illustrate one other thing before we get into how we control force. And what I'm going to show you guys is things about this sort of tension curve right here. All right. When you apply one action potential to a muscle, the amount of force that you get from that one action potential is called a twitch, or it's twitch force, or twitch torque, or something, depending on what you're actually measuring. Okay, on that force tracing, right, we're going to go action potential, and I get, well, that did not go well, right, and it goes up, and then it comes back down. We can look at the shape and the speed at which force rises and falls and learn things about that muscle fiber once we've applied one action potential. And so what we want to look at is on the front side are things called rise time and time to peak tension. Okay, time to peak tension is from when force production starts until it reaches the top. Okay, how many microseconds or milliseconds does it take from the initiation of a cross bridge to peak torque? Rise time is the same thing, but it measures the slope from 20% to 80% of force. So it's trying to measure this kind of linear straight line portion right here. These two things are a function of the myosin ATPase. The myosin ATPase, right? So fast twitch fibers will, because their myosin ATPase is faster, they will have a steeper and faster increase in force. We also measure something, we call it half relaxation time, but it's from peak force halfway back down to baseline. Okay, half relaxation time. This is a measure of CIRCA function. Right, and so what I'm showing you guys up here is if you look at, say, a muscle in your eyelid versus the muscle in your thumb, the first dorsal interosseous muscle, versus a muscle, let's just say, in your soleus, okay? Note the different shapes of the twitches. Eye muscle is really fast. Quick up, quick down. Very, very fast twitch, right? Your thumb is somewhere in the middle, and then here in your soleus, right, is probably outside of your diaphragm, the slowest muscle in your body. Slow to rise, slow to relax. Okay? So we can use these twitch characteristics, or the shape of your force curve from an action potential, to learn something about your fiber time. Okay? To learn something about fiber time. If you want to know, we do this in my lab every day. Okay? But this is really important because these shapes, though, are determined by what's actually going on in that signaling pathway. Myosin ATPase enzyme, calcium ATPase enzyme, how long and short are the active state, and how quickly can we recycle our cross bridges. Okay. Okay. We're going to put that concept, though, the active state and these things, to use in an interesting way when we modulate force production. Okay. So sometimes when we recruit a motor unit, we need a little bit more force, but we don't need as much force as we would get if we turned on a second motor unit. So we have another strategy that we can employ, and it's called neural rate coding, or firing rate, or firing frequency. And what this is a measure of is the frequency with which the motor cortex sends action potentials to that motor neuron. Okay? What you see in the first tracing up here, every vertical line is an action potential. That's an action potential being sent down an axon. So it's an action potential that has cleared through the alpha motor neuron. These are all measured in people's first dorsal interosseous muscle. So it's the muscle that makes your index finger do this and push out. We stick little needles, electrodes into that muscle, and we record the electricity out of those electrodes. And so in the first one, they're doing like 2 grams of force. We're getting more and more force out of the same motor unit here. And so what you will see is this very infrequent action potential at low force. And then when we need more force, it stays recruited, but we increase that firing rate more and more. And as we need more force, we send more and more action potential. This is how the nervous system controls the volume on things. All it can do is say action potential or not. So when it wants to gradate what's happening, it does that by saying more or less frequent action potential. Okay? And so we get more force out of this, and I'll show you guys why in the next slide. Because you get an action potential, you release calcium. If there's enough time between my action potentials, I pull all of the calcium back into the sarcoplasmic reticulum. But if I get an action potential, and then I get a second one before all of the calcium has been pulled back in, then I have whatever is left from the first action potential that hasn't been pulled back in, plus whatever I get from the second one. So now I have more. Okay, there's a little bit left, and then I add some more on top. And then I get a third one. So now I've added more and more and more. Okay. And so what happens then is I can progressively increase, by increasing firing rate, the amount of calcium that is out and the length of the active state. As I make the active state longer, I get more force. As I release more calcium, I get more force up to a certain point. At a certain point, you basically swamp the ability of circuit to pull the calcium back in. And you swamp the ability, like you cannot get any more calcium to leave the SR. Okay, I'll show you guys a picture of what that looks like in a second. Okay, does that make sense? Okay, does that make sense? All right. So when we graph all of this, okay, we take the actual force production that we were getting from the previous slide and we graph it out, we get a relationship that looks this way. What you guys see here on the x-axis is something called stimulation frequency. This is the frequency of action potentials being sent from the motor cortex to the alpha motor neuron and then to the muscle. We measure electrical frequencies in something called hertz. Okay. Think of this to make the math easy. 10 action potentials per second. 20 per second, 30, 40, 50, 60, 70 action potentials per second. All right. And then on the y-axis, we're graphing force production as a percentage of maximal force. And so what you guys can see is this measurement was taken from a person's quad muscle, and we artificially apply electrical stimulation. We artificially give them action potential. Anybody ever been to physical therapy and had what they oftentimes call it rushing stimulation on a muscle? This is rushing stimulation, but it's to the nth degree. Okay, we are putting big electrodes on your quad, and we zap you basically as hard as you'll let us, with as much juice as you will let us. Okay, and we get a muscle contraction, and so at low firing rates, we get a low amount of force. We get increasingly more as we release more and more calcium. But then at some point out here in this particular group, at about 50 hertz or so, going up and increasing the frequency, we don't get any more force. We max out how much calcium can be released. Okay. And so this is called the force frequency relationship. This relationship looks different in people that have fast twitch, lots of fast twitch fibers, and lots of slow twitch fibers. Okay? Lots of fast twitch, lots of slow twitch, they're gonna look different. Okay? Why would it look different? What's different between fast and slow twitch that would have an effect here? Anybody want to guess? Trinity. I'm sorry? Minus an ATPase, yes. That's going to play a little bit of a role, but let's imagine that this is a fast twitch person. And then if we were to also graph a slow twitch person, they go up and then they plateau off at like 25 hertz rather than out here at 50. Okay. The shape is going to be basically the same, but it's going to go up and it's going to level off a little bit sooner. So minus an ATPase is different. That's going to make your twitch look a little different, but on this one, what else might be different? Is there another enzyme? Kendall?
Well, I don't have an enzyme, but is like calcium reuptake more efficient?
Yes. And that is driven by which enzyme? Somebody help me? By SERCA. Very good. When SERCA is faster, like it is in fast twitch fibers, you relax faster between your action potentials. You pull more calcium back in between successive actions. And so that actually leads to, right, limiting the increase in force that we get in between these things. Okay, so fast twitch fibers will reach sort of plateauing out on their maximal force at a higher firing rate than slow twitch fibers. Okay, so this is a really interesting sort of observable phenomenon. So again, if you come to my lab, we can build a curve that looks like this on you and compare you to everybody else in class and give you a relative thing, right? Like we could compare Lily and Ainsley and Sarah and Morgan together, and within the four of you guys, say Morgan has likely the most fast twitch fibers and Lily has the least or something, right? I can't tell you you're 80% fast and 20% slow based upon this, but I can give you relative to everybody else that we test. Okay. So again, this is form and structure imparting how we control force. Okay. So what you see here is just a graphical representation of what we've been talking about. Okay. You get one action potential. Here's your twitch. The blue line represents force. I get one action potential, force goes up. Calcium starts to be pulled back in. Oh no, here comes the second action potential and release more calcium. And so now force goes up more. And then it starts to relax, right? Here comes the third action potential up again. Okay. And then as they become more and more frequent, you get this sawtooth, ping, 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 and it increases, right? But at some point they become so frequent, they're right on top of each other. So there's no time for SERCA to really pull any calcium back in between the action potentials, and you get this flat, what we call a complete tetanus or a fused tetanus, this flat contraction. Okay. And all of this is how we use the nervous system to control calcium release and how the calcium is what gets us across. Right. Anytime you need to do a contraction, as I wave my hand, I recruit a certain number of motor units to do that movement, and I recruit every motor unit at a similar but potentially somewhat different firing rate to precisely control how much force I get out of every individual muscle fiber, so that I get just enough force and no more. Okay. You guys ever think about recruiting a motor unit? When you do that, do you ever think about, okay, I need to send 10 action potentials to the second, right? It just happens. It astounds me all the time that we are so good at this, okay? We're so good and so precise at how we do all of these things. That the motor cortex can send all of these thousands and hundreds of thousands of action potentials to just the right place, at just the right order, at just the right magnitude to let us do whatever it is that we're doing. Okay? And that's just for simple movements like walking. Actually, walking is really not simple. Walking is actually very common. Okay? But it just blows my mind the way the nervous system is connected to our muscles. Okay. So I'm going to show you guys this graph, and you don't have to like memorize it or anything. But I show it to you because this is my single favorite graph in all of neuromuscular sort of physiology right here. Because it illustrates, I think, what I just explained to you guys about how we use recruitment and changes in firing rate together to control force production. Okay. So I tried to explain to my daughter, so there's a place in Oklahoma City where you can go and they have pizza. It's called Sauce. I don't know if everybody from Oklahoma's ever been there. They also have, we live in Midtown and there's a bar. I'm sure you guys have never ever been to a bar. But there's a bar that has old video games. I've forgotten what it's called. Okay. It has old video games. But anyway, we were at Sauce having pizza with some friends a couple of weeks ago, and they have a bunch of like old video game machines that kids can go and play. And they had a game that I played on an Atari, which you guys Google what an Atari is, when I was like my daughter's age. So this was back, in like the early 80s and everything. It was called Missile Command. And it was, these things that you didn't have phones, but everything was like, there would be a dot and a line, and the dot would like move up, and you had to like line another dot up and like shoot the missile down. It was the 80s. We were worried the Russians were going to shoot a bunch of nuclear warheads at us and all of that. So maybe not a whole lot has changed in 40 years. But this graph reminds me of that. Just a complete aside. And I'm sure that's all lost on you guys. What we see here, this is force production on the x-axis. Okay. Lots of strength, very little strength. The y-axis represents the firing rate, okay, of each one of these lines. Every line represents one motor unit. These are data from a single person, and so you can imagine they jabbed like 50 needles into this person's first dorsal interosseous muscle, okay, right here. And what they're recording then is do the least amount of force that you can manage. And so you get one motor unit recruited and it's firing at 8 action potentials per second. Now slowly increase the force. Before we get a second one, we crank up the firing rate in that one motor unit up to about 14 here. We're getting more force. Then we continue to crank that one up. It's like, we need a little bit more force. Let's go and get a second motor unit. And that one starts back off down here today. And you just keep adding, ramping the firing rate in existing motor units up to a point, and then adding new motor units at low firing rates on top of each other to collectively give us whatever force we need. And then you tell them out here, press as hard as you possibly can. And you turn them all on, and you turn them all on it. This is probably a pretty slow muscle at about 20 to 24 hertz. Okay. This is what happens every time you do any contraction. This is happening thousands and thousands and thousands of times. Okay. You make adjustments in this. You hold your arms out. You're like, oop, I'm wobbly. I push you. You make an instant adjustment. You start to fatigue right from holding your arms out. You make an instant adjustment. And this is how we control force production. This is how we learn to do all of these different things. Okay. I'm amazed that we can sit up, much less walk and run and sprint and do a whole host of other things, because this is what's happening. Okay. All right. So how am I doing on time? Of course, you let me talk about my favorite stuff and I go a little bit long. Okay. So that's the nervous system. How big is your muscle? How much of that muscle can you recruit? And at what firing rate and what kind of action potential frequency can you send there gets us force? Okay. Those are the two big things. The next couple of things you got to talk about, though, are going to be what I would call mechanical factors. They're the properties of the muscle contraction that we're doing. that when you overlay how big the muscle is and how much you can recruit and activate on top of it, also play a role, but a lesser role in controlling force production. All right. And I struggle with this, but I'm going to show it to you anyway. All right. What you guys see here is some very classic data from the 1960s. This is a thing that illustrates what we call the sarcomere length tension relationship. And what this shows us is, imagine you have a sarcomere. Everybody do this. Sarcomere, right? Dad's hands, right? Sarcomere. Overlap the actin and myosin together, okay? And so as we have some overlap, we form cross bridges, and they want to try to slide by each other like this, okay? If you have something that's really heavy and you're doing an eccentric contraction, it wants to try to pull them apart out like this, okay? It's going the opposite direction. What we know from dissecting down on individual sarcomeres is that the degree with which actin and myosin are able to overlap and connect with each other plays a role in how much force that sarcomere by itself can generate, okay? And so that is illustrated in this very top curve. On the far left is a very, very short sarcomere. So a sarcomere that has been shortened as far as it will go, okay? Boom, like this. It cannot go any farther, okay? You get very little force. As we widen it out, we're going to get into a place where there's more ability for actin and myosin to overlap. We're going to get more cross bridges, therefore more force. And then at some point, as it gets stretched, we begin to lose the ability of actin and myosin to connect. We get fewer cross bridges and force goes down. So it looks like this. Somewhere in the middle is what we call an optimal sarcomere length for actin and myosin interactions. And that's illustrated here. This is the very short sarcomere. Here we are in the middle, and there at the top, you can see we have very little overlap. Where we've got like one heavy filament, one myosin filament, and then like two actin filaments that we connect. But this is happening all across the muscle in every sarcomere. Okay? And so what we illustrate with this basically is that as sarcomere length changes, your ability to produce force from those sarcomeres, regardless of how many sarcomeres there are, regardless of how much motor units are recruited or calcium is sent, that change in sarcomere length can affect force production. Okay? Okay. Everybody say that. I'm going to leave you with the thing on a Friday, okay? We're going to do one squat, just one, okay? Do one squat with me. Ready, guys? All right. Down. That feels nice. And up. Okay. Now, maybe I lied. Maybe we'll do more than one. But as we go through this, all right, in my quads, are my quads when I'm up, are they short? Are they in the middle? Or are my quads stretched and lengthened right here? Short. You all agree with that? Okay. When I go, y'all don't have to, but when I go to here, what's happening? I'm stretching them a little bit. When I get way down here, what are they? Let me see if I can do it all the way down. Keep my heels down. Okay. Now, think about through that squat. Okay? You thought about short, a little stretch somewhere in the middle, very, very stretched. Think about it as it relates to strength. Okay? Where am I strongest in my squat? Is it here, here, or here? The middle? Okay? When you do a squat, where do you get stuck? The bottom. When your muscle is at the longest length. Okay? If you can get it to like 45 degrees, you can probably get it the rest of the way up, right? We've all seen the people. Maybe it's been you. I'm squatting. I'm totally squatting, right? I'm really squatting. I'm doing this. I'm totally squatting today, right? Somewhere my father, the football coach, is rolling his eyes at people doing all of that, okay? So, does less strong, strong, less strong, look like this? Okay. Sit. Really hurt my TAs. Oh. So. It's important. To generate trust in relationships that you're honest with each other. Right? So I have to tell you guys that I just lied to you. Okay? I just lied to you. And I did it for the purposes of teaching, not because I want to be deceptive in any way, shape, or form. Right? What you guys just did and said is 100% correct. Weaker, stronger, weaker. Okay? That part's absolutely right and absolutely true. Okay? And it looks like this. It looks like the sarcomeres, as we go from short to longer to longest, are going through all of this, and that's what's changing our force production. Okay? But that's not true. Okay? That's not true. That's not why it looks that way. This is a thing that is real, and a thing that has very little contribution to force production in your muscles, because your sarcomeres almost never, ever get either shortened or stretched enough to be outside of that kind of middle optimal length in your everyday life. Okay? So this is a real phenomenon. This is a real thing that happens, but it's mostly a thing that we can show and make happen in isolated sarcomeres in a petri dish or test tube. Okay? But it does match up with, and think about it with if I was going to curl the same, right? Lengthen, weaker, stronger, not quite as strong at the very, very top. Okay? It matches up with whole muscle changes in length or changes in joint angle. Okay? So if this isn't what's causing that to happen, do you guys know what it is? Anybody have any guesses? What is it that makes that happen? Why am I weaker at the bottom of a squat versus somewhere in the middle? Why am I weaker at full elbow extension than I am right here? Man, it is torque, that's right, but what is the thing that makes torque different than force? Who said physics? Moment on. Who said biomechanics? Anybody in biomechanics? Two of y'all? Okay. The moment on. You guys have all been on a seesaw before in your life? Or you've used a shovel or something, right? Okay. Our joints create levers. Okay? And weirdly enough, as you move a joint at your elbow or at your knee or at your hip, that lever actually changes length as you move across the range of motion. Okay? And that's because when you look at the axis of rotation at the joint and you measure the distance from that axis to where the tendon inserts on the bone on the other side, as it moves, that distance actually either shrinks or increases. In some joints, it stays pretty similar, but like in the elbow and the knee in places, it changes. And so what's happening is the muscle's the same size. You recruit the same motor units, you fire them at the same firing rate, but our ability to actually transmit that force through the tendon onto the across the joint changes based upon what the joint angle is. Okay, and we'll pick up from there on Monday. All right. Y'all have a good weekend. Make good choices. Think about moving arms. Think about linking relationships.